Alright, welcome to our next lesson on slope fields. This is lesson 6 in chapter 6. So take a moment and jot down this information. Of course, feel free to paraphrase. So slope fields, what are these? Well, these are graphs. Okay, let's circle this keyword. These are graphs made up of tiny tangent line segments which map out the general shape of the solution curve of a differential equation. So these are going to allow us to see the general shape of this solution curve without knowing its actual equation. Now recall that if we're talking about a differential equation, we are given a derivative, and derivatives give us tangent lines at any point. So just a little illustration here. In black I have the solution curve, alright, so that's like your y equals equation. And in blue I drew in little tangent lines. So imagine that black curve not being there. Imagine if all we saw were just those tangent line slopes. Well, we would be able to get a feel for the general direction of that solution curve based on those little tangent lines. Okay? So likewise, if we saw something that looked like this, if we had a series of tangent line slopes that looked like that, all right, we would expect the curve to move in that direction. Okay, so the tangent line slopes show us the direction of our curve. Alright, so copy down this example. This is a pretty simple example. We are given a basic differential equation of dy dx equals cosine of x. Now this is not a difficult equation to solve, right? To work backwards and find the y equals solution graph. But right now we're not focused on its actual solution. We're focused on the derivative being cosine of x, and we're not asked to solve it. We're asked to create a slope field for x values between negative 2 pi and positive 2 pi, y values between negative 4 and 4. So we're just going to sketch this. Doesn't have to be perfect. Alright, so we have our graph set up here. So what we're looking to do is create a slope field, and that means we're going to have little tangent line segments drawn in. So what does that look like? Well, I'm going by increments of pi over 2 here, or 90 degrees. Let's start with x values of 0. So if we go back to this differential equation, this derivative equation of cosine of x, all right? So if we're talking about the x value of 0, all right, cosine of 0 we know is 1. So every single time that the x value is 0, this is really telling us that the slope is 1. Because remember, dy dx is a derivative, and a derivative represents a slope of a tangent line. So the slopes of all the tangent lines are going to be 1 when x is 0. So at all of these points here, all right, where x is 0, we're going to draw in a tangent line slope of 1. So I'm going to do it right through negative 4 to positive 4. Okay, so if it's a slope of 1, we know it should be angled at a 45-degree angle. It's not super steep, nor is it super flat. Okay, so let's find another key value, such as the cosine of pi over 2, or 90 degrees. Okay, well, the cosine of 90 degrees is 0. So that means for pi over 2, I know that all of my tangent line slopes are going to be horizontal here, right? So the slope would be 0. So I'm going to draw in these little tangent line slopes there, all right, with a slope of 0. Okay, so do the next one, all right, the cosine of pi. Cosine of pi is negative 1. Okay, so now we're going to go through. So it doesn't matter what the y value is, as long as the x value here is pi, we know that the slope is going to be negative 1. So we're going to again draw this at a 45-degree angle, because that's what a slope of negative 1 would be. Okay. Next would be 3 pi over 2. So the cosine of 270. Okay, well that's 0 again. So draw that in. And then finally, cosine of 2 pi is the same as the cosine of 0. That was 1. So we're going to draw in our tangent line slopes of 1 all the way down. Okay. And so we need to go back a cycle to negative 2 pi, so you're just going to repeat what we just did. Okay, so take a moment and get that down. So it's the same as what we see from 0 to 2 pi. We're just repeating it. We're just backing it up a cycle. Okay, so let's make an important point here. Notice how the general shape of this graph equals the sine curve. And that sine curve is the solution to this differential equation, right? When we integrate cosine, we get sine. So you can see, hopefully, that this is resembling our sine curve. Okay, so if we were to use those tangent line slopes to guide our drawing of the function, we would see that it's the sine curve. Now we have a whole family of them, okay, as opposed to one particular curve, all right? So this just shows us the general shape. We can see the general family. All right, last example here. We are looking to make a slope field once again, but this time our differential equation is dy dx equals x plus y. So notice right away how we have not only just an x, but also a y. All right, and then once we have that, we're going to look to sketch the graph of that particular solution passing through to 0. And by the way, we're going to do this sketch between -1 and 3 for x values, and then -3 and +3 for the y values. So with the last example, when our differential equation was just cosine of x, it was pretty easy to quickly draw the slope field because we were only talking about x. So for example, if x was 0, we said how the slopes there were 1 for all of the y values. So we were able to quickly draw a slope of 1 for all those y values when x was 0. Well, here there's a little more work involved because we're going to have to add the x and the y for each point to then determine the slope. All right, we've got to figure out what that slope number is, and then we'll sketch it. So let's set up our graph. All right, so I set up the graph here. And one thing to point out, anytime AP wants you to make a slope field, you're going to see the points kind of darkened like that. It's going to be very clear where the individual points are, where you're expected to draw the tangent lines through. Okay, so it just makes it easier for you to know where to place them. So expect to see those darkened points like that. All right, so it's a bit easier for you to do this. Now, rather than just sitting there point by point and trying to figure out what it's going to be, what I suggest you do is make a table. All right, and so here's what the table would look like. So what I really have here is a 5 by 7 grid. All right, and each box here is representing the 35 points that we see here on our graph. So for example, this top left box is going to represent the point -1, 3. So what I would like you to do is go through and write the coordinates of all of your ordered pairs there. All right, so you're literally going to write all of your ordered pairs. And by the way, you're not going to see a slope field where you're going to have to do 35 points like this. Usually it's, I don't know, 10 to 15 that you might have to do. All right. So I guess I'm just a very cruel and mean individual for making you do all this. But anyway, so you're just going to write out your ordered pairs. All right, and so keep in mind these are giving us x's and y's. All right, and then we're going to squeeze into each of these boxes what the slope would be. Remember, according to our formula up above, our slope is found by adding x and y. So, for example, with my first one here in the top left corner, my slope would be 2. Okay, and you can see, guys, that there's going to be patterns emerging. You can see just as you look at your points here, of course, there's patterns everywhere. So it's really easy to jot them all down, of course. So the slopes, same thing, you're going to see patterns. So take a moment, add all of your x's and y's, write down your slope values. All right, so once again, yes, it's tedious, but it makes sketching it a piece of cake once you have these slopes written out. So yes, it's a sketch, but at the same time, while it doesn't have to be perfect, we want to be as accurate as possible. So as I look across my first row here at the slopes of 2, 3, 4, 5, and 6, of course we want these segments to be getting steeper. So the slope of 2 is going to be a little bit steeper, of course, than a slope of 1. All right, and then the 3, and then the 4, and then the 5, and then the 6. Right, so it's looking pretty darn vertical towards the end. All right, as we draw these through the point. Okay, so as we go here from left to right, it's getting steeper looking. Okay, so you're going to do this for all of your points. Draw in your slope field. Okay, so there's our slope field, and again it's showing the general shape of our solution curve. Now we don't actually know what the equation is of our solution curve. We've just mapped out the general shape. So the last thing we're asked to do here is to sketch the particular solution that passes through 2, 0. So 2, 0 is right here. Again, use a different color if you have one. Okay. So if we are going to follow this and look at the general direction of this based on these tangent line slopes, okay, you can see there's a spot where it's going to be bottoming out. All right, and then we're going to be following that general shape here. Okay. So keep in mind we have a whole family of curves shown. So if it's passing through this point here, you have to look at the ones around it, follow this general curve. We can see that there is a slope of 0 where it's going to have to bottom out. All right, so this would be an estimate for our solution curve passing through the point 2, 0. Oops, I almost ended this video without saying bye-bye. Okay, bye-bye.